Hello? Great. Hey, can you hear me? Yeah. Awesome. I hardly understood anything before, but let me say bonjour. Okay. So actually, I'm going to make two presentations today. The first is about TensorFlow.js, but since many people express their interest in machine learning on source code in general, I'm going to partially repeat presentation which I already gave on .ai in Paris about machine learning on source code. But yeah, I'll start with TensorFlow.js. So let me begin with a quick introduction to JavaScript and web technologies in general. First of all, if you think that JavaScript is a language, actually it's not really a language, it's a trademark which belongs to Oracle, because JavaScript was trademarked by Netscape. Netscape was bought by America Online, then America Online was bought by Sun, Sun was bought by Oracle, so after all it belongs to Oracle. So JavaScript is not a language, it's a family, or let's say a generic name of a series of languages. The standard is called ACMA script, and JavaScript is a subset of ACMA, and every engine implements JavaScript a bit differently. So it's a wider term which tries to mimic ACMA script, but not really. So I guess most of the people here are ML engineers and data scientists. I heard these words. This means you should be familiar with Python. And I guess fewer people are familiar with Node.js and JavaScript. But you may have heard about it. So Node.js is a technology to run JavaScript in the server or on the desktop, but not in the browser. And Node.js is built on top of V8 JavaScript engine. I think it can swap the engine to the one used in Edge on Windows, but most of the time it's used with V8. And V8 compiles JavaScript in time. It's called JIT, just in time. And usually, especially when Node.js appeared about 10 years ago, everybody thought that it was the best environment for web development, because it solved the very famous 10K problem when you had 10,000 requests per second and you needed to serve them. But it appears that the most recent release of async.io in Python 3.7, made by Andrei, don't remember his surname, he's from Belarus. He is the original author of async.io. He made some improvements. He added UV loop. And actually, now Python with async.io is 2 times faster than Node.js. So it's just not true. Python can be better for web development. At the same time, Python is a very complex language to execute. It has many features, so it's really hard to compile it with some improvement in speed. You may have heard about PyPy, which is an attempt to JIT Python, but it struggles. It really struggles to achieve the performance because, as I said, Python is very advanced. And yeah, you are going to support all the features, otherwise nobody will use your JIT. So in contrast to Python, JavaScript is much simpler language. So it's much easier to JIT, to compile it, and to execute it. So generic Python is considerably slower than Node.js. And if you want to work with strings, if you want to read files, of course, plain, pure Python will be much slower than Node.js. If you don't trust me, go to benchmarks game on Debian and you will see the benchmarks. However, again, since we are ML engineers and data scientists here, we work with Python scientific stack, which includes NumPy, which includes Skippy, which includes other libraries. And they are very well optimized and they are very performant, especially if you build them right. But there are just simply no such libraries in JavaScript, and you're left with typed arrays, and it's very hard to achieve any peak performance in linear algebra with JavaScript. This is why currently really few people do data science or machine learning seriously with JavaScript, just because there is no ecosystem. But no more, because now we have TensorFlow.js, which is able to accelerate linear algebra in a web browser or in Node.js on your server, and it reaches roughly the same performance as you get in Python using the same TensorFlow routines. Also, thanks to TensorFlow.js, we can now even do automatic differentiation in JavaScript and train, at least in theory, train and run machine learning models. So this is a quick introduction to TensorFlow.js. And it started last year. It's a very young project. Used to be DeepLearn.js. Now it's named TensorFlow.js. And the team behind it is rather small. It's roughly 10 engineers from Google Brain. The team will grow next year, but currently it's only 10 people. And the official features are as that. You can develop machine learning in the browser, you can run existing models, or you can retrain and do transfer learning. However, the reality is a bit different, because actually now you cannot really do serious development in the browser, even using TensorFlow.js, because it just runs too slow. I'm personally the guy who runs Python for machine learning, and I know how to compare, and the current training speed of machine learning models in the browser, even after this fancy WebGL acceleration, is 10 to 20 times slower, so no, you don't use it, no. But however, if you want to do data science and ML with Node.js, which is different because you're not doing it in a browser, you're really doing it in your server, but with JavaScript frontend. It's actually getting viable because, as I previously said, JavaScript is much easier to accelerate. It has a really nice execution engine in V8. So the routine operations which you perform in Python before actually training the model, JavaScript is better at these operations because it's faster. So I can see some meaning in starting developing machine learning models in Node.js. And one of my demos, I will have 2 demos today. The second demo will actually show you how to do it. So regarding running existing models, again, everything is not really obvious because the serious models, they are at least 50 megabytes, 100, 200, 1 gigabyte. And imagine that you have to download 100 megabytes over your Wi-Fi just to run machine learning model. It's just not usable. The more or less normal size is 20 or 30 megabytes. Everything which is on top, given the real connection speeds which we have today, you will have to wait so long that it just makes no sense. So although it is possible to run a huge model and the modern browsers do not limit you in your operating memories that much as they used to a few years ago, that's still like not for the real user. Can be just made for fun, but not for production. So TensorFlow.js has 2 API levels, the core and Keras. I will describe both API levels in more detail. The core API is just copied from TensorFlow. However, there are some changes. The most important ones is that you don't have sessions. So TensorFlow has a concept of a session, and you execute your graph always under a session if it's not eager. And eager mode in TensorFlow tries to compete with PyTorch and build the execution graph on the fly. In JavaScript, you do not have any sessions, and you just run the computations instantly and get the results instantly as well. You don't have any low-level neural network APIs, which you may use in TensorFlow, TF and N. And most importantly, you have to deal with your memory by hand, and you need to convert your existing models to a so-called web-friendly format. I will say a few words about memory management and format on the next slides. So first about the format. Currently, TensorFlow has 7 formats, which you can use to store your model. The simplest one is a graph definition. It's a model which is serialized to protocol buffer. Then, as you train the model, you checkpoint it, and checkpoints can also be used to load a model. Then you have summary for TensorBoard, then you have metagraphs, you have saved model, you have model definition for TensorFlow Hub, and finally you have Keras format, which is HDF5. So already 7, and even the official documentation kind of confuses them sometimes. And now we have the 8th one for TensorFlow.js, which is really a combination of these 7 with an addition of the JSON manifest, which describes the model. Also, the weights are sharded. The thing is, it's a bit hard for a web browser to download 30 megabytes in a single shot. Everything may happen. You can have network error, and you don't want to download 30 megabytes again. So they shard weights by small portions, let's say 4 or 5 megabytes, and you download each chunk independently. So unfortunately, we have to deal with another format. So as for the execution modes, as I said, TensorFlow.js can run in WebGL, in the web browser. The linear algebra operations are accelerated using WebGL. Or you can run it in Node.js, but then it will delegate all the operations to libTensorFlow, and the speed will be exactly the same as you're used to using normal TensorFlow with Python. So I mentioned manual memory management. The motivation is that you have to dispose your tensors by hand when you don't need them anymore. And this is not something we are used in Python, which doesn't deal with it. You just code it, and something is automatically disposed afterwards. This happens because Python has reference counting, and the lifetime of the object is more or less determined, well, if you don't have these circular loops with references. Usually you don't. So as long as your tensor in Python loses the scope, the reference count is decremented and the object is freed. JavaScript works differently. JavaScript has a garbage collection, but that's only half of the problem. The other half is that there are many JavaScript engines, and garbage collection is implemented differently in each of the engines. And you cannot really tune or influence the lifetime of your tensors. Imagine that you allocate a fully connected layer with hundreds and thousands of neurons on WebGL in your web browser. You don't need it, but you really don't free it because you rely on GC, and it stays in your memory like for another 5 minutes, because this is why GC works. It collects every few minutes. And then you run out of memory very quickly because you're going to create tensors frequently. So this will just not work in JavaScript. So unfortunately, you have to dispose by hand. And this is an example of the source code in JavaScript, which demonstrates manual tensor disposal. You have a special function called TensorFlow tidy, which removes all intermediate tensors while they are being created in the inner scope, and you just get the one which is the result. Unfortunately, if you want to implement a layer or any other function which is using TensorFlow in JavaScript, you have to deal with tidy and dispose quite often. So authors are very well aware of this problem, and this is why they have TensorFlow buffer. So tensors are immutable, you cannot change them because they're pinned to device memory and you use them mirrored to the device. TensorFlow buffer is mutable and it's not really a tensor, but it converts to tensor. So tensor buffer is stored in your operating memory, you can change it, and when you need, you can convert it to tensor. So it allows you to not really allocate much memory on heap constantly. This is especially handy for batching. And again, I will show you how in my live demo very soon. So speaking about Keras API, I know that most of the TensorFlow users are not really using these low-level APIs because let's say straight, it's very hard to use, they're very complex, and you have to take much things into account. So instead, most of the people, at least who I know, they use higher-level abstractions. There are quite a few. Keras is one of them, probably the most popular. And before you ask, Keras Python package is not the same as Keras in TensorFlow because the interface is the same, but implementation is really different, although it's written by the same author. So TensorFlow Keras is related to François Chollet, but not really implemented by him. It's implemented by a team at Google Brain. And TensorFlow.js implements Keras in TensorFlow and not Keras Python package. So it works, I checked it, it's nice, but it doesn't have cuDNN, and this is a serious drawback because if you take convolutional neural network seriously, you are going to use cuDNN acceleration. The speedup is very substantial. So for now, they don't support it, unfortunately. I mean, TensorFlow.js on the low level, of course, it does it, but the Keras API on higher level doesn't have cuDNN LSTM cell, doesn't have cuDNN RNN cell, so on and so forth. And also, it's kind of not really polished. I tried it, and sometimes, for example, recurrent neural networks leak, and you cannot create big, for example, sequence-to-sequence models with it. I stopped at roughly 200 neurons limit, and after 200 neurons on a single RNN layer, for some reason it explodes and goes out of memory, although it's really few. So for now, they are still kind of polishing it and fixing the bugs. The bug is reported here. So I hope soon they will not have the memory leak. Not sure about cuDNN plans. And this is all I wanted to say about TensorFlow.js API. And it's time to show you the demos how it works. The first will be in the browser. Not very advanced from theoretical point of view. I'll just load Mobilenet version 2 and try to classify an image in the browser, not really using Python or anything else. So I'll press a button, load tf.js, which will import the TensorFlow.js library in JavaScript. And it takes around 100 milliseconds. That's fine. Then I load the model. And loading the model takes from 1 second to 3 seconds, depending on your luck and internet connection. Mobilenet version 2, as you know, is pretty well small and optimized for, well, you know, mobile devices. So it's a good example to use in a browser. At the same time, even this small model takes you 1 or 2 seconds to warm up and to be loaded. Let's classify an image. I'll press the button and I take a random image, open it, and it is classified, and it finds the cowboy hat on the guy, and it runs pretty fast in 70 milliseconds. So it works. Let's see at the source code. I need to increase the font. I wonder how can I do it. Oh yeah, nice, it works. So for those of you who don't know what I just did, I opened the developer tools in the web browser. You have developer tools in Firefox or in Chrome. I'm using Chrome because I'm used to that. And I do everything with a single script, with two scripts. The first is just a JavaScript file with ImageNet classes. As you know, ImageNet has 1000 classes, and they are really indices, so you need to convert indices to proper names, and this JS file just contains the mapping from indices to names, nothing really to look inside. So the whole thing is executed here. It looks like it's long, but actually it's not, just because the font is big and also the view is not so long. We take two constants, the path to the model, which is a JSON file. Remember that this web-friendly format consists of three parts: protobuf with network topology, JSON manifest, and sharded weights. So we point to this JSON manifest, and this is some leaking information which we could really load from the model, but we don't because we are lazy and we want to cut corners. So we have several functions. This is service one, which reports the status, nothing to look. The load tf.js function just loads the tf.js JavaScript from the CDN. Again, nothing exciting. Load the model is using TensorFlow, which we just loaded in the previous function. You have this function tf load model. Whoa, no. Tf load model, which you feed the path, and you get the model, which has a method predict, and you feed it some data, and you get the result. So we load and predict on zeros at once because this is a so-called warming up. You allocate tensors in WebGL. You compile everything because WebGL acceleration involves shaders. It's the only way to accelerate. It's not CUDA, it's WebGL. So you compile shaders every time, and this takes some resources. So this is just, you know, a first run to really just warm it up. You may notice a wait, which is a feature of the recent JavaScript. So the function is asynchronous, and instead of writing a callback and turning your code into spaghetti, you can just use a wait and pretend that it is executed sequentially, although it's not. So it's a nice syntactic sugar. So as easy as that. The next function, called loadImage, loads the image, which we just took from our file system. Nothing interesting. And most of the things happen in predict. So we load our image. Come on, we load image from our image tag in HTML. The image size is hard-coded to 224 by 224. Again, we should really resize it here because we don't know the initial size. Also, we should crop. We don't do this because we are lazy, so we just take it from the image. TensorFlow.js only works with 3 data types: It's a 32-bit integer, it's 32-bit float, and if I'm not mistaken, it's a Boolean value. So the only way to work here is to convert pixels to floating points. Then we do some normalization. We subtract the mean. And then we reshape to a single sample in a batch and feed it to Mobilenet predict. And it returns you the raw logits, everything which you need. The rest of the code is very boring. You just take these logits and sort them, take the biggest 5 and display them in your HTML. So everything is super easy for applying the model, and training it is, of course, much more complex. There are more examples how you can take a model and load it and do something with it, or even do fine-tuning, the thing which Google emphasizes. Don't know why. So you can go to this link and look at more examples. And I'm passing over to the second live demo, which is more tricky. I'm going to use node.js and actually train a model using this thing. You may wonder why the lights are here, because it's just a fancy light. They're not really used for anything. Also, I'm going to use iJavaScript, which is a JavaScript backend for Jupyter. By default, Jupyter works with Python. I'm used to Jupyter. I don't like writing JavaScript in IDE, so I want to use Jupyter with JavaScript. So I install iJavaScript and get JavaScript support in Jupyter. Hope it works. So this thing is an external GPU, and it's connected to my laptop using Thunderbolt 3. Because this laptop doesn't really have any NVIDIA GPU. Let me increase the font. Let me show you that we do run with NVIDIA GPU inside. And yeah, we do. So we have one. It's not a very modern or fancy one. It's GTX 1070, but it's enough to demonstrate. I'm going to run everything inside a Docker container because this is not my laptop. My laptop is in skip hole because I forgot it there a few days ago. So this is Hugo's laptop. If anything doesn't work, that's Hugo's fault. So I will use the container which I prepared a few weeks ago just for this case, which runs Jupyter, JavaScript, TensorFlow already installed inside. It launched Jupyter, and now I need to go to localhost 8888. And we get Jupyter. That's nice. And we go to notebook directory which we mapped, and it contains the notebook which I prepared for the live demonstration. So as you see, we see JavaScript Node.js here because we are running iJavaScript and JavaScript engine in Jupyter. I've already done these steps which are needed to download the dataset. I'm going to solve a text classification problem. So it's not really a hardcore one, but it involves recurrent neural networks, attention, and sometimes even normalization. Sometimes, yeah. So, yeah. The first step is to import everything. We are going to use file system, the package to parse CSV because the dataset is in CSV. This stuff is needed to make the code asynchronous and pretend that it is executing sequentially and use await. And this is TensorFlow itself. So I run it and it executed. This huge code is needed to actually load the dataset. This is not related to machine learning, really, although it uses some TensorFlow to do random permutation, because at the end of each epoch, you need to shuffle your data. Yeah, I just execute it and get the class. And the next step is actually loading the dataset. It will take 10 or 20 seconds.
How big is the data? How big is the data?
It's 150 megabytes. Oh, nice. I didn't see this message before. Okay. It wants some require from me. Whatever. So you see, it is not really finished executing, because now it's going to CUDA, initializes everything. I didn't really include it to the first version of the notebook, because Google developers, when I asked them explicitly in the issue, told me that you should not do this because now it should just automatically work. For now, unfortunately, it doesn't, so you really have to execute it. So let's wait. It usually takes around 60 seconds. It is doing something terrible inside, I guess compiling CUDA. Well, at least it's working. Well, I can, but it will work slower. So while it is doing something, I guess compiling and increasing the... Oh, yes, it's finished. Thank God. So the next function is called create model, which creates the model with some hyperparameters. So as I said, we are solving a text classification problem, and I read the text by character by character. And also, since the dataset is a tweet dataset, I have a length limit which equals 140 characters, which is very nice for me. I don't really need to care about the variable length of the text, whether it's very long or short. I just put 140 and forget about it. So this is TensorFlow and Keras. If I use Keras, I would use input starting with a big character. Here we have input starting with a small character because it's JavaScript, and the JavaScript naming convention is lower camel case and not upper camel case for class names. So we create an input. The D type is 32-bit integer because TensorFlow doesn't work with unsigned bytes, unfortunately. Then we use embedding and just one hot encode each character. And then we add our LSTM layers. They are pretty straightforward. Some forget bias, which does some improvement according to the documentation. I trained without it, and with it I don't see any difference, but whatever. And we return sequences. If you used Keras here in Python, you would also use dropout. Unfortunately, LSTM in TensorFlow.js doesn't support dropout as of now, so the only way to use dropout is to apply it after the sequence is generated. So just remove some elements from the sequence. Then there is an option to train a bidirectional network, which is always good. So we add the bidirectional layer with LSTM we just created. And here you see that we can use dropout after the sequence is generated. Also, we use attention. There are two modes in which we can create our network. The first is a debugging mode with which is called char RNN, where you just generate the next character. I use it to debug the model and ensure that everything works fine. You don't have any bugs in your data pre-processing, in your batch generation. And as long as I debugged everything, I switched from char RNN to actual classification. So the second mode is called classification. I add attention. The implementation of attention is a classic one. We just multiply by attention the output from our last bidirectional LSTM layer. And we train everything with, well, binary cross entropy, because we do binary classification. In our case, we have a tweet data set and we do sentiment analysis, so each tweet is either positively or negatively expressed. And we do it with a simple dense layer. We compile the model with add-on optimization, print the summary, and return it. So as you see, it's exactly the same as we would write in Keras. Apart from some features are missing, such as dropout. So if you know how to write Keras architectures, you can just transfer your knowledge to JavaScript and train it in node.js. So this is needed to train. Skip this one and go directly to classification training. And the core is here. We run model fit. As you remember, Keras has model fit generator, which allows you to fit models on unlimited sizes of your data set, just because you cannot place all your data in your operating memory. Unfortunately, TensorFlow.js doesn't support it at the moment, but you can simulate it by your calls to model fit. setting the number of epochs to 1, disabling shuffling, and setting the batch size to your to size of your data which you feed to model feed. It works the same, of course, not very fancy, and there is an issue which I created to actually add feed generator function, and the developers agree that it is needed, but it is not yet added yet. So everything is straightforward. We take the next training batch, we feed it to model feed. Sometimes we validate and print some metrics from validation. Also, we print the result of prediction of the sentiment of this hard-coded string, just to make sure that the network works sane for debugging. So let me run this network. So we solve a classification problem, bidirectional with attention. Number of LSTM units is 64. If you set it to 96, you will get out of memory. So this is why 64, just because I cannot set more. So we train it for 1 epoch, because as you would expect, this character level text classification network overfits like crazy without dropouts. And we don't really have dropout here, so we get what we get. Oh, I need to execute the train classification. And now run the training. Come on, create model is not defined. I told you so much about it. Didn't execute it. So it created a network. This is a summary. I'll try to decrease the scale. I hope you still see something. So this is the summary, and it shows some progress. This is the number of batches left to process, and this is the number of batches processed. Let's wait for about 2 minutes to get to 101. And while we are waiting, I can proceed with my presentation. And only the summary is left. Oh no, I didn't mean it. So to summarize, using TensorFlow.js is very easy. For applying the model, it's just 2 lines to load it and to run prediction. To train it, it's the same as Keras, so it's really easy to run. It's still in very early days. There are bugs. Sometimes you have leaks, and sometimes it just misses some features. But proof of concepts on the official website and the ones which you can code, they will actually work, because everything is well tested, as you would expect from Google. And unfortunately, with addition of another 8 storage format, TensorFlow is getting even more complex. And I have a feeling that it's not the end. And the most important insight is that many JavaScript coders which don't really know anything about machine learning are going to use TensorFlow.js for reason and without the reason, and just abuse the whole machine learning with JavaScript. This is all I wanted to say about it, and let's see what we have here. Still no 100. But the speed is roughly the same as for Python. So it's not really retarded, it's just the GPU is not very performant. Also, I'm running RNN, so RNN are always harder to train on a GPU, especially if it's not cuDNN and just a regular implementation. So these are my contacts, and the presentation is online, so you can go to the link or scan the QR code if you will, and view it on your device. And I still have some time to tell you about machine learning on source code. I'm going to skip some slides because some of them are pretty generic and I don't feel that I have to explain what they mean. So I want to say a few words about code naturalness, which is a core concept, one of the core concepts in machine learning on source code. And it means the relation between how we write source code as a human and how it is executed. When we code, we do it in a certain way. We name entities in a certain way. We place comments. We structure the source code in a certain way. Also, from the machines which executes the source code, it really makes no sense, and it really ignores our names, our comments, and our structure. On this example, you see a class in Python with 3 methods: connect, query, and close. And the connect method has DB name, user, password, host, and port arguments. So just having some prior knowledge of what this code can do, you can think that the class can be named a database because, you know, connecting, database, DB database name should be a database, or at least something very, very, very much related. And this is the naturalness. Although we don't really look inside what the methods are doing, we just look at the names. We already have some model in our mind what the source code is doing. And this is another example. So we have some generic class with names, with method names bar, buzz, and do. Arguments also do not really provide any insight. So we think that probably this source code is bad, just because it's very generic, names are bad, probably a junior engineer wrote it. We don't like it, right? Again, it can be perfectly correct from an algorithmic point of view. It can be doing the right thing, but we just cannot understand it just by a quick glance at the source code. So identifier embeddings is a way to capture code naturalness and encapsulate it into identifier embeddings, right? So each name which you encounter in source code, variable name, class name, function name, whatever, it can be mapped into a dense vector so that identifiers which are related to each other will be on short distance. Euclidean distance or cosine distance, how do you define the space? I will skip this. Supposedly you know what is an embedding. So the core question is, how do we estimate this color product between our vectors which correspond to identifiers? And I'm going to explain very short how do we estimate it. We calculate the explicit co-occurrence matrix, identifier co-occurrence. So on this matrix, each cell's value corresponds to how many times the corresponding pair of identifiers appeared in the same context. How do we define a context? We have the source code which is already structured. So we are going to use this structure to define co-occurrence. This is a sample source code snippet. And we are going to process every identifier which we encounter here. We split by naming conventions. Sometimes it's not enough, and we split using a recurrent neural network. It's actually our paper at Sourcet about it. And also we do some normalization and map some very similar identifiers to the same, just because to reduce the matrix dimensions. So step number 1 we take the whole visibility scope and we connect each pair of identifiers in this scope all to all. If some identifiers appear more than once, the corresponding value is multiplied by the number of times we observed this identifier. So .ai was a conference for, let's say, casual ML engineers, so I represented a occurrence matrix as a graph just because it's, it's more obvious for them. Anyway, this is how it looks like. The thickness and brightness of the edge corresponds to how many times the pair of identifiers appear together in the same visibility scope. So then we proceed deeper and we just take a single method from the class. We repeat exactly the same procedure and we sum the key occurrences which we had on step 1 and on step 2. And this is what we get after step 2. Some of the lines got thicker and brighter because we have a very big value for the corresponding pair. Then we start traversing the abstract syntax tree. We visit the function signature, do the same. Then we go scan the function line by line, block by block. We take identifiers, increment, until we finish everything and end up with the occurrence matrix. I name it incidence here. So the usual way to embed entities, words, identifiers is using the pointwise mutual information. And the way of defining the scalar product as pointwise mutual information is a classic one. It is well studied. It is defined in the original paper about word2vec. So not really exploring anything new here. And you can calculate pointwise mutual information from the values of the co-occurrence matrix. This is why we did all these steps and calculated co-occurrences. And the rest is done by a representation learning on explicit matrix algorithm. This is how a typical matrix on natural language looks like. It's very unbalanced. You have a tiny core of frequent words, and the rest is a huge long tail. So we are going to use a swivel algorithm. You may have heard about GLOF. Swivel is roughly the same. It was presented in 2016, if not mistaken, by a group of Google researchers. It is very practical. It is very engineering oriented. It splits the matrix into shards, and it load balances the items between the shards so that they contain roughly the same number of non-zero elements. Of course, the shards are also sparse. And also Swivel does some nice quality tricks which are described in detail in the paper about how do you estimate PMI for each of the shards, for each cell in the shard, how do you synchronously and stochastically update the overall matrix. The problem was with rare words, you don't have enough information, so you need to kind of augment. So all these tricks are described in the paper. Swivel improving embeddings by noticing what's missing by Shazir et al. I'm skipping the dataset extraction, and these are the results of such an identifier embedding. It really has all the properties which you would expect from natural language identifiers embeddings. For example, you can scan for nearest neighbors to foo, and you get other metasyntactic variables, cooks, buzz, wibble, buzz, so on and so forth. You can do the same analogies. Of course, as in the original paper, most of the time actually it doesn't work, so I found examples which work, but there are many examples which do not work. But sometimes it works and you get this nice knowledge extraction. Also, it captures typos because programmers often place misprints. Not all of them are native speakers. Some words are misspelled in the same way over and over and over again. Also, you have British English, you have American English, they're a bit different. So it groups words with typos together, and receive is close to receive, gray to gray, callback without L to callback with K instead of CK, so on and so forth. So this one works very well. Yeah. Also, you can use the embeddings for suggestions. So this is a screenshot from PyCharm. We have a settings class with a get method. So we already typed def and s. And what are we going to type next? Probably something related to settings and get, right? But of course, PyCharm has no idea what we are going to do. It is a machine without any soul. So we do a simple query in our embeddings and get these results. So the most probable one is set, because we have get and settings. But also we can type save, step, sneak, sum, and SSL. So although some of them really make no sense, such as sneak or SSL, they're still better than the original suggestion. Let's see if we finally trained. And we did. And we already have 75% accuracy, and our control phrase, which is awesome, wonderful evening in the prison, is positively aligned. So this is all I wanted to say. Thank you for listening.
Thanks, Vadim. Are there any questions? You can ask questions in English. Vous pouvez poser vos questions en français. On va traduire aussi. Et on est en live stream, donc micro obligatoire.
What is the aim of TensorFlow.js? Like serving models in production in the web browser, or do something like federated learning over web browser for the world, or just for fun?
So I would say that the official main goal is to run pre-trained models in web browser for whatever reason, for object classification, detection, and whatever else you can, each query to your server allocates some resources, in your data center. If you are Google, you don't care about it, but if you are not Google, you're going to use your GPUs, and if you have many clients, you need to have many GPUs. And probably you don't want it, and you want to run all the heavy lifting on client side and just cut costs very much. And even Google wants it. So according to the examples, even Google wants to run some at least simple visual problems in web browser. The second goal which I see is which can work. It's not official one, but I like it, is to actually do ML with node.js in Jupyter and TensorFlow, because JavaScript sometimes works much faster than Python, so it may work.
More questions?
Thank you for the conference. And there is a tensor board is Sorry, the English. Yeah, TensorBoard will be in production for TensorFlow.js soon, or there is something for TensorBoard?
Indeed, it makes much sense to integrate it to TensorBoard. Unfortunately, the main author of TensorBoard left Google and founded his own startup. Well, probably Google is big, so they will find another one. But I don't know about any plans of integration between those two. But yeah, indeed, it makes much sense.
So I've got two questions related to the memory management. So the first one is when on pre-processing. So how difficult is it to build some data pipelines? So if you have a lot of data in your data sets.
So modern JS is asynchronous by nature, and the existing ecosystem is very rich for that. So building pipelines should be very easy and also, enjoyable. I expect it.
Okay. Nice. And the second one is how difficult is it to train a large model like ConvNet in large image? So you said that the out of memory error is so common with with this tool. So is it difficult to train large models?
So indeed, I had memory errors with recurrent neural networks, but fully connected and convolutional ones seem to be better debugged, and I think it should be possible. Also, there is an official example which does fine-tuning of a serious, rather heavy object classification network, so it should be possible.
Okay, thank you.
So I have a question, so I'll jump in since I have the mic. On the code part, did I understand correctly that you're basically doing weighted bag of word? Well, so that you take all of the subtrees of each parse tree, do weighted bag of words on each of them, and then do clustering on all of those vectors. Is that an oversimplified but reasonable summary of what you said?
So I don't really have bag of words. I just build the co-occurrence matrix. So I connect each word to each word and increment by one the corresponding cell in the matrix. But indeed, I do it across all ESTs, all files, in all open source data which we have, and we have roughly 200,000 top start repositories on GitHub. So this was our data set. Okay,
so it's just it's not using vectors to do it, but it's just whether words co-occur in any given subset of the subtree of the AST.
Yeah, as you know, it's proven in the original Word2Vec paper that it is equivalent to actually doing it not explicitly but implicitly, and taking a sliding window and reading text by this window, right? We don't have text, we have source code, but we could do the same with a similar approach. We just found that explicit algorithm is more practical because it scales with the vocabulary size.
Right. Cool, thank you. More questions?
Yeah, I had one question about libTensorFlow. So it's using libTensorFlow, right? TensorFlow.js, you said, on Node.js?
Yes, it delegates all the work to libTensorFlow on Node.js.
Okay, and so for the dropout, is it just the binding that's missing, or why don't you have dropout if it's already using the lib?
Yeah, the thing is you can load arbitrary complex model in TensorFlow.js, So it's just the Keras implementation in TensorFlow.js, which misses some operations, misses some features. Yeah.
Oh, okay. Thank you.
So I hope they added.
Any more questions? We still have a little bit of time. We also have a lot of cheese and wine and stuff. Questions? Il y a des questions? Okay, so let's thank Vadim again for a good presentation.
Okay.
Since given your profession,